So my name is Susan Potter, and I'm going to be your host or guide on a whirlwind tour of trying to remove the dysfunction from operations by trying to add reason and meaning. And we're going to do that using techniques and ideas from functional programming. So the agenda is I'm going to try and make a case for the importance of being reasonable. And by reasonable, I mean adding reason to your code, your infrastructure code. And I'm going to do that in two ways, a slight academic case and then a business case. And then we're going to review functional programming 101. How many of you have done functional programming to any degree? OK. So it looks like it's a mixed crowd, so I'll kind of go through just sort of some elements that we're going to be building upon in the talk. And it's going to be a very informal sort of introduction. And then I'm going to illustrate different types of reasoning that we get from functional programming ideas and techniques. And then we're going to reimagine package management through this reasoning. And it's going to be something that we can do without actually writing any code at all. And we'll see that hopefully I'll do my job, right? And I'll show you that without writing any code, we can actually make the approach and the design better just by thinking through it. OK, so who am I? So I started as an application developer in 1996. That was my first paid gig. And it was Perl 4. Forgive me, Father, for I have sinned. And I stayed an application developer or system or server developer for about 14 years. And then about 4 years ago, I kind of transitioned into operations and doing infrastructure engineering. In terms of my biases, today, I do like types, and I'm sorry. OK, so there's this quote. Some of you may be able to tell who it's from, but it's basically the required techniques of effective reasoning are pretty formal. But as long as programming is done by people that don't master them, the software crisis will remain with us and will be considered an incurable disease. Anyone know who that is? It's Dijkstra, right? And so my position may not be quite as severe as this, but I think he's interested in the industry improving, and I think all of us are here too, right? So I'm going to make a business case now for adding reason, both informal and formal, but making more, adding more reason than we currently have today, right? And that is, in operations, technical operations that I'm involved in, application delivery is kind of like a key thing, right? We need to be able to provision infrastructure. We need to be able to configure nodes. We need to be able to do that reliably and predictably, right? We need to be able to orchestrate services. And being able to reason about different parts of this is actually really important, especially when a lot of applications are currently being developed in languages that are optimized, shall we say, for rapid development and not necessarily for verification or better techniques or things like that. I currently work in an environment. We deploy SaaS applications for the consumer and enterprise markets in mobile security. I work at Lookout. And I work on a team called Infrastructure Engineering. And we're trying to provide developers with a self-service kind of platform such that they can push their services on their own sort of schedule into production in a reliable fashion, right? Taking care of their dependencies and things like that. We need to be able to support more applications. We're moving from a monolithic application that we built 8 years ago. I haven't been there all that time, but we're moving to a service-oriented architecture, so that's a pretty important need. We've got to spin up new environments all the time for performance testing or for new partners, beta testing and things like that. Data services, we have quite a heterogeneous set of data services: Cassandra, MySQL, Postgres, Redis, Memcached, a few others. I can't even. Elasticsearch. Distributed services, right? Like processing, Hadoop, Storm, and Kafka, for example. So we need to be able to support all of these things, right? So just kind of like solving the stateless server or stateless service or stateless application kind of problem for infrastructure delivery doesn't really work for us, right? Oops. So we need to optimize for reliability. And by reliability, I mean, in the real world, I want to know, is this as deterministic as it can be in the real world, right? The real world means we don't really get determinism, really, for anything. But is it as reliable or as deterministic as we can possibly make it, given the business constraints and the time to market and all those sort of considerations? Scalability, and I mean scale up and down. We have a lot of short-term projects, data migrations and things like that for partners, which are short-lived. And so we need to be able to scale up, but we also need to be able to scale down as well. That's really important for us. And here I said code consistency, and this is a different concern to just general data consistency, which is, of course, a very important thing to consider, right? But for us, when we're delivering infrastructure and delivering applications on that infrastructure, we want to make sure that the application versions that we're rolling out have all of the things that they need in terms of system dependencies, whether that's on the node, like packages, runtime, services, and things like that on the actual node itself, or actual other services that need to be in the environment, right? And that wasn't always the case, right? So the previous solution that we were using at Lookout, which was based partly on Chef and a few other things, we had like a separation of the application code and the infrastructure code. And even though we were doing infrastructure as code, it wasn't, we weren't relating the two very well at all. And so there were numerous cases where we actually rolled out applications, services that needed something that wasn't there, and that was problematic. So have I made the business case? I don't know, that we need determinism, or we need at least predictability and reliability, and those are really important things. We also need to be able to reason about the infrastructure that we're deploying out, right? I'll let you heckle me later, and you can tell me if I did an okay job there or not. Okay, so we're going to quickly go through like functions, and it'll just be a drive-by kind of guide. Yes, I know it's Scala. I regretted it as soon as I compiled the slides. I apologize. So functions, they have inputs. I don't think this is particularly controversial. Here we've got a function with taking 2 arguments on the first line. The second definition is just taking 1. They return results. Again, probably not very controversial. We're actually getting an int back from the add and an int back from the length. Okay, so here we're only depending on inputs, right? Functions only depend on its inputs. And so here we've got a function on the second line that we've defined. And you can think of it as kind of like a defaulting function. We may have read in a settings file or something like that, which may or may not contain a value, right, of a timeout or something like that. But we do have a default timeout defined up here, 30 seconds. So in the first usage of it, we're providing it the default timeout, and it so happens that that particular configuration file that we looked in had a value of 15. So it actually returns 15, as we expect. And in the other case, that configuration file, that application is just going to use the default, right, which is 30, as we expect. But we're just depending on our inputs at this point, right, in terms of the function. definition. We can use other values, and those values can be functions. Functions as values, that's kind of an important idea. So here I've just done a type alias, which is just defining a predicate, just to clean up my types. And yeah, Scala isn't the prettiest, I apologize. So we've got these functions is and not. We're just trying to evaluate whether or not this predicate function that is passed in, so we're passing in a function, right, as an argument, evaluates to true or false. And then here, the bottom two definitions, it's LTN, which is less than n, right? So I pass in an n value argument, and it kind of defines a new predicate. So we're returning a function in this case, and that predicate is, less than that n that we passed in, right? And then we can use that function later on in another function, like we do in the last one here. And so functions also return the same result given the same inputs. This is probably the most important slide, even though it's the least impressive. If you take one thing away from you, it's this idea, right? So every time you give it the same inputs, it should always, always, always give you the same result. And this is called referential transparency. And some people call this pure, but pure can mean so many different things. So I'll just call it referential transparency. And it's a horrible name because it's, whatever. But it's less ambiguous. OK, so questions. Was that too basic? Was that OK? Did I lose anyone? OK, good. OK, so just another drive-by, like composition. Function composition in this case. So we're going to return to the command line, UNIX. And the first kind of pipe that we're defining, the first command, we echo without the new line, hello tilde tilde tilde. And then we send that the output of that to the sed command. And that's just going to remove the tildes. It looks like there's a space after the tilde, but I think that's just the font. I apologize. And then we send the result of that, which should just be the hello, the capitalized hello, and then we convert all of the lowercase characters to uppercase, and that's what we would expect. And we can kind of reuse the first part of it and then pipe it to another command and just count the characters, and that's what we get there. Notice that this is character-based, and we're driving this all the way through multiple file descriptors, right? So function composition, it's the same thing, right? The difference is that it's value-based, and we drive it through functions. We have to have the functions line up, but that's the same as the commands anyway, right? So if the output of one command is not what the another command later on expects, then you're going to get weird results. So again, two upper, we define the length. We've got the sanitize function, which we're just replacing the tildes. And then we've got the myfun definition here, myfun0. We're saying you run this sanitize function, and then on the result of that, two upper, right? And then we can reuse the definition of myfun0, and then apply len to the result of that. And so again, you see the results as we expect when we apply those functions. So what is the purpose of that? Actually, the purpose of showing you this is that we can actually build bigger and bigger programs using both function composition and passing functions around and returning functions from other functions, right? We can express a whole bunch of things, and we can eventually build up a meaningful program, a program that actually matters, not just these silly little examples that fit on a slide. And we do this by depending on referential transparency, and referential transparency gives us the ability to reason mathematically about these functions. And as a result, we kind of build a more solid foundation. Questions? OK. OK, so reasoning. So I kind of alluded to this, but there's this thing called equational reasoning. It really doesn't mean all that much, actually, but it's kind of useful because if we do have referentially transparent functions, then we can substitute in a name for it and clean things up. So for refactoring purposes, this is actually mightily useful. If there's a repeated expression all over your code base, if you know that it happens to be referentially transparent, you can just lift it out, just add name it somehow, however you do that in your language, and then just add that name and then pass whatever arguments it requires in there. That's not necessarily true of non-referentially transparent code, right? You might have side effects that will bite you in places I can't say. So basically, we've got the substitution rule that we can use, right, as part of equational reasoning. We can even use equational reasoning to determine whether or not something is referentially transparent as an informal proof, right, as an informal way of reasoning or showing that we can't reason about something. And the really cool thing is that we've got the ability to do simple testing. So in the other room, we've got Justin. And he's a very cool chap, and he seems to know his stuff when it comes to testing. But as I understand it, the topic of his talk is talking about how you write meaningful tests, right? My guess is he's thinking about side-effecting code, right? And having to test that, because that is complicated. And it is a necessary evil if you don't build your code this way, right? Using referentially transparent sort of contract, right? And so you kind of avoid the need of having to learn what test doubles are. So those, spies, mocks, fakes, dummies, stubs, you can just forget all of that, right? Because you just pass in the arguments that you want to use, and then you assert the value that you expect it to return, right? So testing in the imperative world where there's side effects everywhere, this tends to be what your test suite looks like. You end up sort of mutating the software under test just to be able to validate peripheral behaviors on your of your assertions, right? Just to be able to write your specs and to be able to run those specs, which seems kind of a little bit backwards, but it's kind of a necessary evil. But it seems to undermine the whole verification process of that testing model, right? We don't actually need to worry about that when we're testing referentially transparent code. Now, that doesn't mean that your whole code base has to be that way. You have to pick what is actually the most useful, right? What are the pieces of your code that you actually want to be able to reason about? What are the things that you want to build that way? Because it does take a little bit of time to learn. It does take a little bit of time to change, right? The error of our ways. And so here's an example of equational reasoning. We've got this value x, and we're just calling reverse on that x, right? But we get the same value if we just put the actual hard-coded value in there as well, right? And that will never change, right? We can call that many, many times, and that's not going to be a problem. Now here, we can see a problem, right? I mean, obviously, I'm using a var, right, not a val. But we've got this var of age, right? The driver from the airport yesterday told me that I look 27, so I put that in there. I was quite chuffed about that. And so then we've got this other definition, this incra definition, right? And we're just going to increment the age by 1. And then we're going to return the new age, right? And obviously, this is not referentially transparent because when we assert that incr should equal 27, we get false, right? And then when we inspect it later on, we get 29. So I aged 2 years just this morning, yeah. And so axiomatic reasoning, I'm not sure if this is the right terminology, but this is, seems to be what co-workers have called it. So if you start out building a system, you want to assume some very basic things, no more than necessary, right? And those things are called axioms, right? Like, for example, John here, he would assume that the network is reliable, right? Yeah, that's always a great idea. And then, but this allows us to kind of like specify properties, right, and infer things, right? So from these basic axioms and these basic assumptions, we can kind of build up, you know, through actual reason, right, like logical reasoning, various deductions and propositions and things like that. About our system. So basically we should be asking at different parts of our system, what can we guarantee and what can we not guarantee? And both of those things are actually really important. Telling me what you cannot guarantee is actually just as illuminating sometimes as what you can guarantee, because typically the guarantees that we can make about software aren't very strong. But the things that we can say we can't guarantee are kind of interesting. Right? So here's a very small example, but this cropped up in some Python code actually, but I rewrote it in Ruby. In AWS, there's this notion of a VPC. It's a virtual private, I can't remember, whatever connection, I don't know. And so this, you know, it basically a network, right? And we're supposed to give it a cider, right, or cider. I never knew how you were supposed to pronounce it. And so one engineer wrote, it accepted this hash for the initialize function, right? Now in Ruby, initialize means this is the constructor, right? So you're constructing a new value of VPC every single time it goes through that. Can you guarantee that it's a valid instance? You should be able to guarantee that it's at least a well-formed instance value, right? And of course, we can't do that in this case, right? Because we're inferring way too much. So instead, a better approach might be to actually build up types, right? Okay. I did tell you, I did warn you that I do like types. I'm sorry, but if we restrict that what can go, what can be given as the argument, and it's well defined and it's well formed, then we can actually know that it's whenever we construct a new value of VPC, we actually get something that's usable back, right? Some other forms of axiomatic reasoning, these are very, very basic ideas. I mean, examples. If we have a one-to-one function, so this is where you've got a value in your input, and it goes to a unique value in the output, and that they kind of all map to each other, right? The domain and the codomain, the input set and the output set. So in this case, we've got two lower. We take an uppercase char, and we return a lowercase char. In that particular case, we actually know that there is a one-to-one correspondence, right? So we know that there must be an inverse, and so we must be able to write the two upper, right? When we've got a function that's onto, which means we may not occupy the whole codomain, right? We may map only to a subset of that. Then we can go back to the possible sources, right? And then when a function is into, right, it means that we should be returning an option of that codomain set, right? Because it doesn't always map to everything, right? To anything at all. So just to recap, right? We found some potential design level problems, right? And these are perhaps trivial examples, but they could be extended, right? And this is all without even really writing code, or at least even running code, at least. So generic reasoning, some people call this parametricity, but I think parametricity means something very, very specific. So when we're reasoning on generic type functions, the less we know about the types, the more we can tell about the function. And this seems a little bit weird, but this is, again, we can find design time bugs, but this is kind of like something we can use to validate our designs and our APIs, right? So here we've got F0. Anyone know any possible implementations of that? Are there any? Yes. So a gentleman over here said identity. So there's nothing we can say about A, because we know nothing about A. It's parameterized on A. And as a result, we can't do really anything interesting on that A, because there's no information about it. So the only possible definition is identity, right? F1, it so happens that there's only two possible definitions, and one isn't that meaningful because we're not using both arguments. And so in the F1 case, we accept the value of A, type A, and the second argument is a value of option of A. An option just expresses whether or not something may or may not have a value. It may be nullable, right, we'll say. And then we return an A. In that case, right, the only meaningful definition is that if the option of A actually contains a value of A, then we return that. Otherwise, we return the first argument. And we already saw that example earlier on. F2 is actually problematic. And the reason it's problematic is because list may be empty, right? And when it comes to normal operating errors, right, errors that you might actually expect in your normal sort of running of software, you should actually encode that in your types, right? And so a better solution might be to return an option of A instead, right? Because you don't know if there's going to be, this might be a head, or it might be like the last element or something like that. There's not much we can do other than return an option of A, or we risk raising an exception, right, which takes us out of the context that we're in. So F4, yeah, that's also problematic, right, because we are trying to extract an A, and we don't actually have another source of A, right? It's only option of A. So there's a possibility that we'll have a runtime exception. So review. Right, so there's a reasoning process here. We assume as little as possible, right? We define all inputs, and we build on top of referential transparency. So anytime you see RT, that's what I'm usually saying. And we derive properties from the domain, right? And we infer properties from generic types. So some of the methods are encoding normal error cases and results, right, like optionality or either is another potential way that we could encode errors. We strive for termination, and this is kind of like we strive for termination, and we try and make sure that it does terminate, except, of course, when it can't, right, when you're building a server. And you should see some Leslie Lamport talks on that then. He talks a little bit about the process of kind of using functions where they terminate, right? And then behaviors for things where you've got an initial starting point and you have transitions between states. And then we strive for referential transparency wherever possible and wherever it's economic, right, for our case. So we should be, there's so much to learn, right? But we can start out informally, like we did in this talk, right? And we build on like the basics. We add formal reasoning as needed and as we learn it, right? And the more we do it, the easier it gets, right? So some examples in the wild. And so this is kind of like a bit of a hand-wavy example, but mainstream package management, it's a bit of a nightmare, actually. So it's based on shared and mutable state on the file system. And I don't know about you, but I don't want to build a system without safeguards, at least, that is based on shared and mutability, right? Yeah, it violates referential transparency. That's how I feel when I see that. So the alternatives are, right, that we can share that state and make it immutable. We can make that state private, and it can be mutable too. And these are both referentially transparent, right? They don't violate that premise. And then we've got we can use expensive coarse-grained locks, and that's actually what most package management solutions, or the mainstream ones that I'm aware of, use today, right? And sadly, right, when they're updating values, they're not able to take advantage of atomic operations on the file system because they're laying out file by file, right? And you can't just like do an atomic operation where you're laying out multiple files at once, at least not in the file systems that I'm aware of. Hybrid, we can also do a hybrid approach without the expensive locks, right? We only lock when we actually need to. So there's actually a system that we use for package management called UNIX, and it does actually solve most of this problem quite nicely in a functional way. So first of all, we define all inputs, right? That's kind of a big deal. By defining all inputs and by making the environment completely clean, right? This isn't necessarily true in most apps or RPM or whatever build solutions that I've seen or that I've been exposed to at least. There's still lingering state in the environment. We can force all clean build environments, right, using a Cheroot solution. We can require explicit inputs, and we get this full dependency definition, right? So if any of the build dependencies aren't there, it will fail to build, right? And so you'll be notified. That's a nice safeguard. So we can ensure referential transparency by in the build steps, we make that space private, and we can build the intermediate build products during that process, right? And it's still, from a high level in the real world, it's a referentially transparent sort of operation, right? Oh, that's a funny thing. So whenever we have unique inputs, we want to derive a unique result, right? And this is an interesting set of properties that results from this. We're able to output to a unique path, and by doing that, right? And that's where we get the shared and immutable part, right? Every time, so any new inputs result in a different path, right? This allows us to install many of the same versions and configurations. So you can even have Nginx, whatever version, and have it compiled in 5 different ways with 5 different plugins, right? Since it uses statically compiled plugins. And you'd be able to just lay them out on the file system without clobbering each other. It has a way of doing symlinks, right? To be able to create your profile and to set up your paths and everything like that appropriately. It also means that we can do binary substitution. So binary substitution is this idea where we can just look up in a binary cache, like a repository that already has this built thing, right, and pull it down, right? And we know that it's exactly what we want because we've found the binary by hashing the name of the package, the version, the build script, all of the dependencies, and all of their dependencies, and their dependencies, and so on and so forth. So we actually know, we have a pretty good idea that we're getting the exact same package content back. So, questions? Yes?
Do you ever run into situations where you have build systems that fundamentally are not referentially transparent, like Xcode when you're building an IPA file, for example, you can't build the same binary IPA file from the same source twice in a row. It doesn't, like, the debug symbols don't work out, so you just can't do it. So does that become too expensive in practice?
Oh.
Some tools really suck, is what I'm saying.
Yeah. No, I get that. No, that's really good. Sorry, I should have mentioned, if you've got a question, there's someone with a mic. So can you actually repeat that, actually?
So like some tools don't generate or can't be referentially transparent. So for Xcode, for example, if you have a source file and you try to build it, you'll get a different IPA file every single time you build it. And that's a problem for crash reporting and other things that really matter. So does this become too expensive in those cases because you might have to rebuild this every single time you need it? Or it might never work in that regard because it's not referentially transparent.
Right. I think something similar occurs with Python objects. There's like the timestamp that's actually encoded in the bytecode. And what UNIX does, at least, is it actually strips that out. Because it's actually not necessary for the actual bytecode itself. I'm not sure. I would have to have a look at that particular case to be able to. But UNIX does actually try to strip out anything that doesn't allow for that sort of the reusability and the shared kind of data sort of thing. Yeah, that's a great question. Anyone else? Yes.
So I'm a little bit familiar with UNIX, and do you have to use it on UNIX OS, or how does that work on Debian or other systems?
You can use UNIX packaging just by itself. It's supported most, Linux distributions that I've seen. There's OS X support, which is support. It depends on the day. So some days it's really great, and some days maybe not. My coworker uses it on OS 10, and we have a counter for how many F words he says that day, and it's usually pretty high. Anyone else? Going once? Going twice? Well, thank you very much.